In this video, we're going to analyze Freddie Freeman's walk-off grand slam. In this year's World Series between the Dodgers and the Yankees, Freddie Freeman in the 10th inning hit a walk-off grand slam. So this is at the end of the last inning, and at the bottom of the last inning, with the bases loaded, he hit a grand slam to win the game for the Dodgers. Also in the series, he tied the World Series record with 12 runs batted in and also hit home runs in the first 4 games of the series. So it's not surprising he got MVP of the series. So using kind of published data about his home run hit, which had a launch velocity of 109.2 miles per hour and also an angle of 30 degrees, we're going to calculate the range, the flight time, as well as the peak height. So we're going to first start off with the range equation. This is not my favorite equation because I feel like the physics in this equation is understanding how to derive it. And so you can check out my other video, which I'll link in the corner here, to see how to derive the range equation. So that really is the physics part of this. But having the range equation, we can plug in the information that we know. 109.2 miles per hour is equivalent to 48.8 meters per second. So we're going to go ahead and plug that in here. So 48.8, that is squared sine 2 theta. So 2 times the theta, so 2 times 30 degrees divided by 9.81. Okay, so this gives us a range of 210 meters. Okay, so that is the range. Next, we're going to calculate the flight time. To do that, I'm going to use my chart to keep track of my data. All right, so I know that the horizontal component of this hit is going to be it's going to be a cosine because it's adjacent, so it's going to be 48.8 cosine 30. And what this does is it gives me the horizontal component of the velocity, which is going to be 42.3 meters per second. There's also a vertical component up here as well, and that's going to be 48.8 sine 30 degrees. And that's going to be equal to 24.4 meters per second. Okay, so I'm going to just kind of bracket that because we're going to use that in a moment. Actually, we're going to go ahead and fill out our table here. So the horizontal, because we're treating this as a projectile motion, which means only gravity force is acting on it. So horizontally, it's moving at constant velocity, and that constant velocity is going to be 42.3 meters per second. There's no acceleration horizontally, and our range that we just calculated over here is going to be 210 meters. Okay. Vertically, it's going to come all the way back down. So the ball's going up and then coming back down. So vertical displacement is going to be 0. And the initial vertical velocity is going to be the y component of the velocity, which is 24.4. 24.4 meters per second. Okay. And the acceleration, because we're treating it as a projectile motion, it's going to be 9.81. We're going to make it negative because I am making up positive and right positive. So there is my coordinate axes to indicate my positive direction there. All right. And then now we're going to solve for the time. To solve for the time, we could use the horizontal motion. And we know horizontally it's moving at constant velocity, so delta x equals vxt. To find the time is going to be delta x divided by vx. And that gives us 210 meters divided by 42.3 meters per second. And we get 4.97 seconds. So that is our flight time. I can then enter that number in here, 4.97 seconds, and vertically also 4.97 seconds here as well. So that is our flight time. And then lastly, we're going to calculate the peak height. what is this height right here? So at the highest point, what is that? So I'm going to rewrite my variables here again. Delta y, vi, vf, a, and t. And the initial velocity is going to be 24. This is vertical velocity, 24.4 meters per second. The final velocity at the highest point vertically will be 0. The acceleration is negative 9.81. And we're looking for the delta y. All right, so I'm going to use a new page to get a little bit more space here. So we're going to use our kinematic equation because we're looking for the displacement and we don't really care about the time. So I'm going to use an equation that doesn't have time, which is going to be v final squared equals v initial squared plus 2a delta y. Okay, so the v final is 0 and the v initial is 24.4 meters per second squared plus 2 times, and this is going to be a negative 9.81, right? Because we're making up positive, so down is negative, and we're looking for delta y. Okay, so we're going to move this over to the left. This is 595, so move this to the left, 595, actually 0.36, equal to, and this is going to be a negative number. This is going to be negative 19.62 times delta y. All right, so divide negative 19.62 on both sides, and delta y, I get 30.3 meters. Okay, so that is going to be the peak height of the ball. So the ball's going through the air, and then so that's going to be my delta y. So the delta y, that is the peak height. Okay, now one thing that you noticed that I did was I assumed that this was projectile motion. I treat it as a projectile motion, but in real life, the ball actually did not go as far as the 210 meters. We calculated a range of 210 meters. However, the actual was about 125 meters. That was how far it actually went. So if we take a look at the difference here, if we took 210 minus 125, 125 divided by 210, we see that it was about 40%, 0.4, or about 40% less than the what we expected if it was in projectile motion. And the reason for that is because of air drag. So the air drag in this case caused it to not go as far. And so a range for air drag about 30 to 50%. And so this would be within that range. So this would be a reasonable range. So although we calculated the range to be 210 meters, it only went 125 meters because of air drag.